Hello guys, and welcome back to another problem about forces and Newton's law. This problem is called the conical pendulum. So let's start. The problem reads, a ball of mass m, 0.4 kilogram, hangs from a massless string of length L 1 meter. So this is the ball, and it's attached to a string from here, and now the other end of the string is fixed to a pivot where it can rotate freely. So the other end of the string here is fixed to a pivot, but it still can go around without any constraint or friction around the vertical axis. As the ball swirls, so we swirl the ball, we allow the ball to rotate or push it to rotate, with a constant speed v, tracing a horizontal circle of radius r, the string makes an angle theta with the vertical. So the ball is going around here, the vertical axis. It's tracing a horizontal circle, so the ball is rotating horizontally, and the radius of the circle r is fixed, and the speed of rotation is constant. Now, in this case, the string is kind of bent from the vertical and makes an angle theta with the vertical. So the angle between the string and the vertical axis at any position, of course, because it's rotating, it's theta. So as the string goes around, it makes the shape of the cone. So that's why we call it the conical pendulum. Now the question is, find the period P of the ball rotation in terms of M, L, theta, and G. So we want to find the period of the rotation as the ball goes in a circle. So let's remember what is the period. If we take a top view of the ball as it rotates, it's tracing a circle of radius r with a constant speed. So as it goes around for a full circle, it covers a distance equal to the perimeter of the circle of 2 pi r. And the time it takes to complete this full circle is the period of rotation p. Hence, since the speed of rotation is constant, I can write that the period is equal to the distance over the speed, so it's 2 pi r over v. But v and r are unknown to me. So for me to find the period, I need to find v and r, or I need to at least to find a relation between v and r so they can cancel out, and I find the period in terms of the other parameters of the question. Now, since the ball is going in a circular motion, it has to have an acceleration. And for the ball to stay on the circle as it rotates, for the radius to stay constant, there should be a radial acceleration, and the magnitude of this radial acceleration should be v squared over r. If the radial acceleration is not equal to v squared over r, then the radius cannot be constant. Either we're going to spread out or we're going to shrink as we go around. So we know this other relation between v and r, that the radial acceleration should be v squared over r. Now, since here we have acceleration, we can think of Newton's law. So Newton's second law relates for me the acceleration to the forces. So before we go on and write Newton's law, let's look at the triangle here and see that r and L are related to theta. So here we have a right triangle because this is the vertical axis and the radius is horizontal. So sine theta is equal to L over r. So this actually allows us to replace r by L sine theta. So now we start with the procedure that we have for the problems about Newton's law. The first thing is we look at the forces acting on the object. The object is the ball. So what are the forces acting on it? We have weight, vertical downward, and we have the tension of the string, which is along the line of the string, and we're going to call it T. That's all forces I have. Now I choose my axes. So I'm going to choose an axis, the radial axis, that points from the ball toward the center of the circle. This direction actually is rotating with the ball as it rotates, but relative to the forces, it's fixed. So it's along the radial direction. The other direction I'm going to choose is the vertical direction because we have weight vertical, so we need a vertical direction, or a direction that has a component on the vertical axis. So now our radial acceleration is in the positive r direction. So I can get rid of the absolute value here. So I wrote AR equal to V squared over R. It's positive because it's toward the center. The acceleration is toward the center. Now I write Newton's law. So Newton's law says that W plus T equal to MA. These are vectors, so I need to project them. Before we project them, let's notice one thing, that the angle that the string makes with the vertical is the same as the angle the string makes with the y-axis. Well, the y-axis is the vertical direction. So this angle is also theta here. Another thing that we notice is that for the radius to stay constant, there should be no motion on the y-axis. So the acceleration in the vertical direction has to be 0. So AY is 0. Now, I can project on the y-axis. On the y-axis, weight is pointing in the negative y-axis, so we have minus mg. Then we have tension here, we have to project it here. So this is the y component of tension. It's positive first, so it's plus t, and it's adjacent to the angle that I have in my figure, so it's cosine theta, equal to the acceleration on the y-axis, which is 0. So I'm going to rewrite this as t cosine theta equal to mg. Now, the projection on the r-axis, or the radial direction. So on the radial direction, we have plus t sine theta. This is the x or the radial direction of x. It's of t. It's opposite to the angle, and it's in the positive radial direction. So I have plus t sine theta equal to MAR. And weight, of course, has no component in the y direction. But we know AR is V squared over R, and it's positive. I can get this as MV squared over R. So here we have t sine theta, and here we have t cosine theta. So t kind of bothering us. We want to get rid of it. So what I'm going to do is I'm going to take the ratio of these two equations. So this over this. So we have t sine theta over t cosine theta is equal to mv squared over r over mg. Now t cancels out. M also cancels out. So we see we don't have any relation, dependence on m. So m is going to cancel out. It shows up in the y projection, and it shows up in the radial projection. In the y projection, it comes from mg. In the radial projection, it comes from the inertia, which is in the form of ma. Now, we rearrange this equation. Now, sine over cosine, it's tangent theta, v squared over rg. Now, I want to replace it in the period to find the period. So what I'm going to do is I'm going to find v from here and replace it in the equation above. So v is equal to the square root of rg tangent theta. Now I replace that back in the period. So I got 2 pi r over rg tangent theta. I can bring r inside the square root. It becomes r square, and cancel the square with the r in the denominator. So we have 2 pi alone, square root of r over g tangent theta. Now, we got the period, but we still have the dependence on r. But we remember what we said earlier, that sine theta is equal to r over L, or we can replace the value of r from here, and we got that the period is equal to 2 pi into square root of L sine theta over tangent theta. So the period does not depend on the mass. It only depends on L and G, and sine theta and tangent theta. But the interesting thing is that if we take a small circle of rotation, so the circle that the thing is rotating on, we make it small compared to the length. It means that the radius is much smaller than L. In this case, the angle theta is going to be small as well. And when the angle theta is small, I can approximate sine theta as equal to tangent theta. And this is actually an approximation valid up to an angle like 10 degrees. So it's not a bad approximation. And when we do that, sine theta and tangent theta cancels out, and the period becomes equal to 2 pi square root L over G. So it only depends on the length of the wire and gravity. That's why actually a pendulum is usually used to keep time, because the period, the time it takes to complete one circle, doesn't depend on the angle on which, as long as it's a small angle, but not exactly on the angle, it just depends on the length of the wire and the gravitational acceleration. Or we can use it to measure or estimate the gravitational acceleration. Thank you for watching, and if you have any questions, please post them in the comments below. Thank you.